There are a million things that we do every day without thinking. Brushing our teeth, drying our hair after a shower, and unlocking our phone screen so we can check our messages are all part of our routine. But what takes place in the brain as we learn a new habit? Old habits, new habits. Sign. What happens in the brain when habits take shape? What's something you've learned to do without thinking? It might be locking the door behind you as you leave, which could lead to some panic later as you wonder if you actually remembered to do it. It might be driving to work. Have you ever had that uncanny experience of finding yourself at your destination without fully remembering how you got there? I certainly have, and it's all thanks to the brain's trusty autopilot mode. Habits drive our lives, so much so that sometimes we might want to break the habit, as the saying goes, and experience something new. But habits are a useful tool. When we do something enough times, we become effortlessly good at it, which is perhaps why Aristotle reportedly believed that excellence is not an act but a habit. So, what does habit formation look like in the brain? How do our neural networks behave as we learn something and consolidate it into an effortless behavior through repetition? These are the questions that Anne Graybiel and her colleagues, from the Massachusetts Institute of Technology in Chestnut Hill, set out to answer in a recent study, the findings of which are published in the journal Current Biology. Bookending neural signals. Although a habitual action seems so simple and effortless, it actually typically involves a string of small necessary movements, such as unlocking the car, getting into it, adjusting the mirrors, securing the seatbelt, and so on. This complex set of movements that amount to one routine action that we perform unconsciously is called chunking, and although we know that it exists, exactly how chunks form and stabilize has remained mysterious so far. To store, or not to store? Learn about the protein that may hold the key to memory retention. The new study now suggests that some brain cells are tasked with bookending the chunks that correspond to habitual actions. In another study, Graybiel and her former team found that the striatum, a region of the brain previously associated with decision-making, also plays an important role in acquiring habits. Working with mice, the team noted that the patterns of signals transmitted between neurons in the striatum shifted as the animals were taught a new sequence of actions, turning in one direction at a sound signal while navigating a maze, which then evolved into a habit. At the beginning of the learning process, the neurons in the mice's striata emitted a continuous string of signals, the scientists saw, but as the mice's actions started to consolidate into habitual movements, the neurons fired their distinctive signals only at the beginning and at the end of the task performed. When a signaling pattern takes root, explain Graybiel and colleagues, a habit has taken shape and breaking it becomes a difficult endeavor. Brain patterns that indicate habits. Although edifying, Graybiel's previous efforts did not establish for certain that the signaling patterns observed in the brain were related to habit formation. They could simply have been motor commands that regulated the mice's running behavior. In order to confirm the idea that the patterns corresponded to the chunking associated with habit formation, Graybiel and her current team devised a different set of experiments. In the new study, they set out to teach rats to press two levers repeatedly in a specific order. The researchers used reward conditioning to motivate the animals. If they pressed the levers in the correct sequence, they were offered chocolate milk. To ensure that there would be no doubt regarding the solidity of the experiment's results, and that they would be able to identify brain activity patterns related to habit formation rather than anything else, the scientists taught the rats different sequences. Sure enough, once the animals had learned to press the levers in the sequence established by their trainers, the team noticed the same bookending pattern in the striatum. Sets of neurons would fire signals at the beginning and end of a task, thus delimiting a chunk. I think, explains Graybiel, this more or less proves that the development of bracketing patterns serves to package up a behavior that the brain, and the animals, consider valuable and worth keeping in their repertoire. It really is a high-level signal that helps to release that habit, and we think the end signal says the routine has been done. Anne Graybiel. Finally, the team also noted the formation of another, complementary pattern of activity in a group of inhibitory brain cells called interneurons in the striatum. The interneurons, explains lead study author Nune Martiros, of Harvard University in Cambridge, Massachusetts, were activated during the time when the rats were in the middle of performing the learned sequence. She adds that the interneurons could possibly be preventing the principal neurons from initiating another routine until the current one was finished. The discovery of this opposite activity by the interneurons, Martiros concludes, also gets us one step closer to understanding how brain circuits can actually produce this pattern of activity.